Welcome back to the deep dive. If you were with us last time, we were really digging into the DevOps world, but from the cultural side.
Mm-hmm. Very much the human element.
Exactly. We were talking about why you need a blameless culture, how to manage toil, and why your SREs have to be in the room from day one at the whiteboard phase.
Right. Not just when things are on fire in production. That was all about the philosophy.
And philosophy is great, it's foundational, but it really only gets you so far, doesn't
It
it?
gets you halfway there, yeah. I mean, you can have the most amazing collaborative culture, but if your technical pipeline is brittle, slow, or super expensive, you're just not going to ship code quickly. It's that simple.
So today we're leaving the culture department, and we're walking right onto the factory floor.
The technical factory floor, where steel meets code.
That's it. You're here because you're looking for that advanced playbook, the specific expert-level tools and strategies, the heavy machinery that lets these massive engineering teams push out changes constantly.
And do it without, collapsing the entire user experience in the process.
Our mission today is to strip away the theory and get right into the nuts and bolts. We're talking about automating delivery, ensuring reliability at an enterprise scale, and even getting into the math behind it.
We've actually broken this down into a pretty logical flow, something that sort of mirrors the software lifecycle itself. We have 3 big areas to cover.
Okay, lay them out for us.
First up, the factory floor. This is all about CI/CD, infrastructure as code, and really digging into GitOps at scale.
Building the thing correctly.
Exactly. Then, section 2, we've got the traffic cop. This is where we talk about the advanced deployment strategies, your blue-green, your Canary, shadow testing, all the ways you minimize risk when you go live.
Managing the release.
And finally, we'll get into the reliability math. This is how expert SREs actually measure risk, how they define success with things like quality indicators, and how they manage that all-important error budget.
All right, that sounds like a comprehensive plan. Let's start at the beginning, on the factory floor.
Let's do it.
Okay, so the whole foundation of high-velocity, high-quality delivery, it seems to hinge on this one core idea. You have to treat everything as a versioned artifact.
Everything. Your application code, sure, but also your configurations, your security rules, your cloud infrastructure itself.
It all has to live inside a managed pipeline.
Yeah.
And that's really where this concept of GitOps starts to take hold.
Absolutely. The core principle of GitOps is, I think, deceptively simple, but it's so powerful.
Which is?
Git becomes the single immutable source of truth for the desired state of your entire system. Full stop.
So if a configuration or a resource definition isn't codified and versioned in Git,
then it basically doesn't exist. Or worse, it's what we call configuration drift, just waiting to cause an outage.
and this is where infrastructure as code, or IAC, makes that principle concrete, right?
Yeah.
Especially with a tool like Terraform.
Yeah, when you're defining your infrastructure, and we're not just talking about simple VMs here, we're talking complex things like network rules or managed instance groups, that definition has to be stored in Git.
And why is that so critical? It's not just about hitting a button and having things spin up.
No, it's about governance. That's the crucial distinction. Storing your IAC in Git is the only way you can get proper versioning. It means you can roll back an infrastructure change just as easily as you can roll back an application code change.
And I imagine it enables peer review for infrastructure, which is huge.
Huge. It forces code reviews before infra changes go out, and it lets you share configurations across a big team without, someone accidentally deleting a database they didn't realize was connected to something else.
Now, when teams are just starting out with IAC, we see this a lot. They try to reinvent the wheel, writing all these custom scripts for just basic project setup. What's the shortcut there?
The shortcut is don't do that. If you're building reusable IAC modules that define what a standard application environment should look like, the recommendation is to leverage the existing battle-tested Terraform repositories that are already available in the Cloud Foundation toolkit.
So you're starting from a known good place.
Exactly. It's fast, it's reliable, it's repeatable. It lets your engineers focus on the application, not on how to reinvent a secure VPC network for the 100th time.
Okay, here's where things get really interesting, and it's a place I see a lot of teams stumble, leading to some pretty expensive mistakes. Let's talk about Terraform state management.
The silent killer.
Right. Teams run Terraform, apply in their CI/CD pipeline, and then suddenly they look at their cloud bill and see 3 identical copies of their entire production stack.
That duplication is an immediate red flag. It's a cost nightmare and a configuration disaster waiting to happen. And it happens because that critical file, the terraform.tf state file.
That's the map between your code and the real world.
Yes, exactly, the MAT.
Mhm.
And if that file is being managed locally on a CI runner or it's just not stored correctly, the pipeline has no memory. It can't access the last known state, so it just assumes nothing exists and tries to create everything from scratch. Again.
So what is the absolute non-negotiable best practice here? How does the pipeline stop this expensive duplication?
The pipeline must be configured to store and retrieve that terraform.tf state file from a robust versioned backend. The standard is cloud storage,
A central, shared location.
a central source of truth for the state. Using the Terraform GCS backend is essential. It guarantees every pipeline run, no matter where or when, is looking at the same map of your infrastructure's current status. That's the mechanism that prevents those parallel stacks.
Okay, so centralized state solves the duplication mess. But what about modifications? Let's say I need to update a critical resource, like a managed instance group, a VAG. I want to change the machine type in the underlying instance template.
Yeah.
Just applying that change can be disruptive.
It can. It's a classic dependency problem in IAC. Terraform sees a resource needs an update, but if it can't modify it in place without downtime, the default behavior can be, well, destructive.
And the goal is always zero downtime during these updates.
Always.
So what's the technical trick here? How do we manage that transition gracefully?
The key is a meta argument you put in the Terraform lifecycle block. It's called create before destroy. When you set that to true on your instance template resource, you're giving Terraform a very specific instruction. Build the new thing first. Spin up the new instance template with the new machine type.
And only once that's healthy.
Only when the new component is healthy and verified, then you can tear down the old one. It's a proactive resilience mechanism you build right into your code. It's essential for preventing those awkward pipeline failures and ensuring uptime.
All right, let's zoom out from a single resource to the entire enterprise. You're running dev, QA, prod, maybe more, all on multiple GKE clusters. You can't just throw your configuration into one giant repository. That's chaos.
That is chaos. You need structure, rigorous structure. This is where we talk about structuring GitOps for enterprise scale, often using tools like Anthos Config Management or ACM.
Because at that scale, structure is what gives you security.
It is. The recommended blueprint is all about separation of concerns. You separate your application code from your cluster configuration, and you separate your cluster configuration from your foundational cloud infrastructure.
Okay, walk me through that. It sounds like a three-part repository structure.
It is. First, at the bottom, you have the cloud infrastructure repository. This is your Terraform. This repo should be shared across the org, but you use different directories inside it for your different environments, a dev directory, a quad directory, a prod directory.
So the Terraform code is centralized, but the environment definitions are separate. This repo would define things like the VPCs, the core networking, maybe the GKE clusters themselves.
Exactly. That's the foundation, and it's owned by the platform team. Layer 2, on top of that, is your GKE infrastructure repository. This is where your Kubernetes manifests live.
So this is for cluster-level stuff, like network policies or maybe a logging agent that has to run on every node.
Precisely. And this repository is also shared, but it uses a different pattern. It uses overlay directories for each environment.
So the base manifest, say, for a standard security policy, is shared everywhere. But the overlay for production might add much stricter firewall rules than the one for dev.
You've got it. And this is how we ensure that specific constraints, like who can access the Kubernetes API, are stored declaratively in Git and then automatically enforced by Anthos Config Management across all of your clusters. It gives you that policy consistency.
That structure makes a ton of sense for governance. But I can imagine the operational headache of keeping those shared repos in sync, especially if you're deploying across different regions. How do you manage that overhead?
The key is really clear ownership. The platform team owns those first two repos. Their job is the platform, period. The application teams, they live in the third type of repo, the application source code repositories.
And these are separated per team or per service.
Right. They should be separate. App teams manage their own code using different branches for different features. This keeps their deployment cycles independent, and it reduces the blast radius if something goes wrong.
Okay, that structure provides sanity. But let's be realistic. An application developer working inside GKE is going to need to spin up a database or a storage bucket. They can't be expected to learn Terraform and file a ticket with the platform team every single time.
That's the classic friction point, right?
Right.
Centralization versus speed. And the solution here is the role of config connector. Config connector is essential because it lets those app teams manage Google Cloud resources directly from inside GKE using the Kubernetes manifests they already know.
So it's like a translator. Takes a Kubernetes manifest, a CRD, and turns it into a real Cloud SQL instance.
It's more than a one-time translator, and this is the critical part for GitOps. It doesn't just run a command once. It creates a continuous reconciliation loop.
So it's always checking.
Always. It periodically checks the real state of that database against the desired state in the manifest that's backed by Git. This prevents configuration drift. If someone goes into the Cloud Console and manually changes the setting, Config Connector will see it and change it back. It ensures Git is always the source of truth for both the app and its supporting infrastructure.
All right, let's move from the foundation to the actual assembly line, the CI/CD pipeline, the engine that turns that source code into a deployable artifact. The sources are really clear on a non-negotiable four-stage lifecycle here.
Yeah, and this lifecycle is designed very strategically. It's all about failing fast. You want to catch the cheap and easy failures first so you don't waste time and money running expensive, slow tests on code that's fundamentally broken.
Okay, so take us through it. Step 1, the fastest and cheapest test.
Step 1, trigger and unit tests. The moment a developer pushes code, your pipeline, let's say Cloud Build, kicks off. The very first thing it runs are the unit tests.
Right, they're isolated, they're super fast.
Super fast. If a unit test fails, the pipeline stops immediately. You've saved compute time, you've saved registry storage costs.
Okay, unit tests pass. What's step 2?
Step 2 is containerization. Only after the unit tests succeed do we spend the time to build the application container. We use the Docker file, we build that immutable artifact, and we push it to a central registry like artifact registry.
So now we have the definitive thing that's going to move forward.
Exactly. Which brings us to step 3, integration testing. The pipeline now takes that brand new container and deploys it to a dedicated, isolated test environment. This is where you run the bigger, slower checks.
Your integration tests, making sure services talk to each other correctly. Your acceptance tests, making sure the business logic works.
Right, and this is also where you'd be testing those reusable IAC modules we talked about. You'd have a Cloud Build trigger for every pull request, ensuring all your infrastructure code is also tested before it gets merged.
And if, and only if, all of those expensive tests pass, then we go to production.
Only then. Step 4, production and smoke tests. The pipeline deploys the artifact to the live production environment, and this is immediately followed by smoke tests.
And smoke tests aren't comprehensive, right? They're just a quick sanity check.
That's all they are. Does the app start? Does it bind to its port? Can it answer a basic health check? It's just to verify that the deployment itself didn't fail in some catastrophic way in the live environment.
That sequence makes a ton of sense for minimizing risk. But speed is still a huge factor. Pipelines can get really slow, really expensive if they're constantly rebuilding everything from scratch.
Yeah, you have to focus on pipeline efficiency. There are 2 big levers to pull here. First, caching.
Caching.
You have to use something like cloud storage to cache your intermediate artifacts. You don't want the builder to re-download massive dependencies or rebuild the same Docker layers every single time. Caching those layers can dramatically speed up your builds.
Then the second lever.
Security and networking. This is a big one. Your integration tests often need to talk to APIs or databases that are inside a private VPC. Things that should never, ever be exposed to the public internet.
And the security team is, quite rightly, going to insist that traffic never leaves the private network.
Right, which creates a conflict. How does your CI tool talk to those services? The robust solution here is to use Cloud Build private pools.
So the build worker itself runs inside my private network.
It runs inside your VPC. This allows it to securely connect to those private APIs without you having to manage complex networking rules or expose anything publicly. It solves the security problem without slowing you down.
Okay, last piece on the factory floor. The finished product, the artifacts. Where do we store them and how do we manage them?
Artifact management and tagging is all about governance. The recommended fully managed solution here is Artifact Registry.
And that's for both container images and things like Helm charts.
Both. Its huge advantage is the native integration with everything else. GKE, Cloud Run, VPC service controls, IAM. It just makes security and access management so much simpler than trying to run your own registry.
So if my team is using Helm to package their apps, they can just use Artifact Registry as a single, secure place for all their deployment packages.
That's the idea. And to get the best performance, you have to think about regional bandwidth.
Meaning?
If your GKE cluster is running in, say, US1, you need to make sure your pipeline is pushing the container images to the registry endpoint in that same region, something like u.artifactregistry.io.
That seems like a small detail, but I'm guessing it makes a big difference.
It's a huge difference. It maximizes your transfer speed, it avoids expensive cross-region data egress charges, and it cuts down latency every time a pod needs to pull an image.
Finally, let's talk about traceability. A bug shows up in production. I need to know, with 100% certainty, which exact line of code produced the container that's currently running and causing problems.
This is all about explicit versioning and immutability. Your Cloud Build pipeline should be configured to automatically include the release version tag from Git directly in the image name. That gives you the link back to the source.
But for a critical rollback, relying on a tag like v2.1 can sometimes be risky, right? Tags can be moved.
They can, which is why for a real emergency, the fastest, safest way to revert is to bypass the tag altogether. You alter your deployment configuration to point directly to the SHA-256 digest of the last known good container image.
Because the digest is unique and can never change.
It's immutable. It guarantees you are getting the exact bit-for-bit perfect image that was working before, eliminating any risk of a tag having been accidentally overwritten.
Okay, we have built the perfect, tested versioned artifact. The factory floor has done its job. Now we hand the keys over to the deployment traffic cop.
This is where the rubber meets the road. This is all about controlling risk as you interact with real users and making sure you can hit the emergency brake if you need to.
It's really about minimizing the blast radius of a failure, and also that mean time to recovery, the MTTR.
Exactly. Have an immediate mitigation plan ready to go.
Let's start with the most dramatic strategy, the one that prioritizes recovery speed above all else. I love the analogy for this one. The light switch. We're talking about blue-green deployment.
Blue-green is your go-to when your absolute #1 goal is minimizing that MTTR. It's an investment. You need 2 identical, fully provisioned production environments. Blue is live, serving all traffic. Green is the new version, waiting in the wings.
And that new green environment is fully deployed and tested internally before any real user ever sees it. Then, with a single change.
Click. The light switch flips. All traffic instantly moves from blue to green.
Okay, let me challenge that a bit, though. If blue-green means I have to maintain double my production infrastructure, 2 full environments, twice the memory, twice the cost, isn't that just prohibitively expensive for most services?
That's an excellent challenge. And yes, it is expensive. The decision to use blue-green is purely a business risk calculation. You tolerate the doubled cost because the cost of downtime is even higher.
So for a critical e-commerce checkout page or a core payments API?
Where every minute of an outage costs you, say, hundreds of thousands of dollars. That high availability from blue-green is not just nice to have, it's a requirement.
Which makes the rollback the big payoff. Let's say you deploy a new feature on a Friday. Monday morning, traffic ramps up, and a horrible load-dependent bug appears, a cache stampede or something. You need to fix it now.
And with blue-green, the quickest fix is not trying to redeploy the old code or waiting for the broken deployment to scale down.
Right.
If you're on GKE, the fastest mitigation is to just update the Kubernetes service selector to point back to the blue deployment.
Because it's still just sitting there, healthy, scaled up, running the old stable code.
It's hot and ready, you change the selector, traffic instantly redirects, and you've achieved a near zero downtime rollback in seconds. That ability to instantly revert is the whole reason you do blue-green.
Okay, so blue-green is great for that instant recovery, but it does have a blind spot, right? It kind of assumes your pre-production test can catch everything.
It does. It doesn't help you find those subtle performance issues or weird user behavior bugs that only show up under real-world production load. For that, we need to get more nuanced. We need Canary deployment.
This is the coal mine analogy. You send a small expendable probe in first to see if the air is safe.
Exactly. You're intentionally introducing a small amount of risk, but to a very controlled population. You deploy the new version, the Canary, and you send just a tiny percentage of real user traffic to it, maybe 1%, maybe 5%.
And this is all controlled through smart traffic routing with a tool like Spinnaker or built-in GKE features.
Right, and the absolute non-negotiable part of the strategy.
It has to be monitoring.
Non-negotiable monitoring. You have to be watching your key metrics like a hawk. Latency, error rates, CPU. If the metrics look good, you gradually ramp up the traffic. 10%, 25%, and so on, until you're at 100.
And this is essential for when you just can't fake production traffic.
Yeah.
When you need real users to validate performance and stability in a way that synthetic load tests just can't.
So let's play out the scenario. The monitoring dashboard suddenly lights up red. A huge spike in 500 errors or latency goes through the roof the second that Canary release goes live. What is the absolute first thing you do?
The first step to minimize user impact has to be to roll back the experimental Canary release.
Immediately. Don't try to troubleshoot it live. Don't add more VMs. Don't try to hot fix the code. Get the bad code out of the production path first. The user experience is paramount, and your error budget is on fire.
Okay, now let's move to the most conservative strategy of all, the one that minimizes risk even more than Canary. Let's talk about shadow testing.
The ghost analogy. It runs silently in the background, completely invisible to the user.
This one always sounds like a massive engineering effort. You're duplicating traffic, but then just throwing the results away.
It is complex, it requires a traffic mirroring component, but the safety you get is unique. With shadow testing, the new version runs side by side with production, and it receives a duplicate stream of live production traffic.
So you're testing against the full real production load, but the key difference from a Canary is
The shadow version's responses are completely discarded. They are never, ever sent back to the end user. The user is completely unaffected because they are still getting their response from the current stable production version.
so if it's costing you money to run, but it's not actually serving users, why would a team choose this?
You use shadow testing when you need to gather detailed performance metrics, latency, throughput, resource use against the full, unadulterated production load, but you cannot accept any risk of user impact, not even 1%. It's the highest degree of safety for performance validation.
So to kind of synthesize all this, if you want to reduce deployment complexity, have that instant rollback capability of blue-green, but also get the risk mitigation of testing with real traffic from Canary, the best approach is often to combine them.
Yes. A combined strategy of blue-green deployment and Canary testing is very powerful. You use the blue-green setup for the instant rollback mechanism, but you use Canary-style traffic shifting to gradually move users from blue to green. It gives you the best of both worlds.
Let's get a bit more into the weeds of how the platforms themselves enable this. How do you do this on GKE?
With GKE, you typically use rolling updates, but if you want that really fine-grained control, like, I want exactly 50% of my pods on the new version and I want to hold it there, a standard rolling update might not be precise enough.
So what do you use?
You use a feature called a partitioned rolling update. It's part of the Kubernetes deployment spec, and it lets you specify exactly how many replicas should be running the new version. It gives you that explicit control to hold a deployment at, say, 10% for as long as you need to monitor it.
Okay, what about on the serverless side with Cloud Run? It handles all the infrastructure, but it still gives you these powerful traffic controls.
It does. So if you want your QA team to be able to test the latest revision without affecting any public users, you deploy it with a couple of flags: no traffic and tag dev.
And what that does is it spins up the new container, but it keeps all the traffic pointed at the old, stable version.
Correct. And it generates a unique tag-based URL for you, something like dev my-service-blah-blah.a.run.app. The QA team can hit that URL directly to do all their testing in isolation. No production traffic goes there.
But what if I have that classic dual-track need?
Yeah.
QA needs their private URL for manual testing, but at the same time, I want to send 1% of real production traffic to the new version to check its performance.
That requires a two-step process. First, you do that initial deploy with no traffic and the tag. That gives QA their private playground. Then you run a second command to update the service configuration, and this time you explicitly split a small portion of the production traffic, say 1%, to that new revision.
So you can have both running simultaneously.
Exactly. Cloud Run's native traffic splitting lets you run that critical live production test right alongside the manual QA effort on the separate tagged URL.
Okay, we're scaling up. We're talking about Kubernetes at expert scale now. This means thinking about reliability and governance in a much more structured way.
Yeah, when you're not just a single team anymore, you have to have guardrails. You have to think about capacity planning, security, and how you keep teams from stepping on each other's toes.
Let's start with capacity planning and auto-scaling. You're heading into a high-traffic event, like the holidays for a retail site. You can't just rely on the reactive tools, like the cluster autoscaler, to save you.
No, that's completely insufficient.
Mm-hmm.
The cluster autoscaler is reactive by design. It sees resource pressure and then it adds nodes. But there's a warm-up time. If you're expecting a huge spike, you will have service degradation while the cluster is scrambling to catch up.
So you have to be proactive. What's the expert-level 3-step plan for getting ready for that kind of predictable growth?
It's a three-pronged approach. First, you verify the maximum node pool size. You have to make sure there is physical capacity configured in your cloud project for the autoscaler to even use. If the max is set too low, it'll just hit a wall.
So check the hard limits first. Step 2.
Step 2, you enable a horizontal pod autoscaler, or HPA. This is for the smaller day-to-day spikes. The HPA scales your pods up and down quickly before the node pressure gets high enough to even trigger the cluster autoscaler. It's your first line of defense.
It's step 3.
Step 3, you perform a load test. You have to validate your assumptions. You run a test that simulates the expected traffic to confirm your resource needs and verify that the scaling limits you set in steps 1 and 2 are actually correct under pressure.
That makes perfect sense. In fact, it seems like the very first thing you should do when preparing for any busy season is to load test the application to profile its performance.
It is the prerequisite. You have to validate your assumptions about how much CPU and memory your app needs before the real traffic arrives. If you get those requests and limits wrong, the autoscaler will work, but your app will still fall over from resource starvation.
Let's talk about keeping teams separate. Multiple teams, multiple microservices, all on the same GKE cluster. That sounds like a recipe for disaster if Team A accidentally deletes Team B's production database.
It is. You need defense in depth. A tiered structure for isolation that uses both cloud-level and cluster-level boundaries to maximize security.
Okay, walk me through that best practice. How do you separate dev from prod and Team A from Team B?
The first and strongest boundary is project isolation. You create your development GKE cluster in one GCP project and your production GKE cluster in a completely separate GCP project.
Because IAM controls are scoped to the project, a leaked credential in dev can't touch prod.
Exactly. It's the best security boundary you can get. Then, within each of those clusters, you use namespaces. You create a Kubernetes namespace for each team or for each application.
And that gives you logical grouping and resource quotas. But a namespace by itself isn't a security tool, is it?
It is not. That's the crucial third layer, fine-grained governance. You must configure Kubernetes role-based access control, RBAC, so that each team's credentials can only access resources inside their own namespace.
So it's the combination. The namespace creates the box, but RBAC puts the lock on the door.
Precisely. Without RBAC, namespaces are just for organization. With RBAC, they become a genuine security boundary inside your cluster.
One last access control question. The CI/CD pipeline, Cloud Build, needs to deploy to GKE. How does it authenticate securely?
The simplest and most secure way is to use IAM integration. You grant the Cloud Build service account the specific container developer IAM role. That gives it just enough permission to manage things like deployments and services, without giving it overly broad permissions like project editor or owner.
We've built it, deployed it, scaled it. Now we have to prove it's reliable. And SRE demands we move way beyond just, is it up or down?
This is the math of risk management. We have to quantify how often things break, how fast we notice, and how long it takes us to fix them. Because those numbers are what drive engineering priorities.
Okay, let's quickly redefine the 3 key time metrics SREs use.
First, mean time to detect, or MTTD. This is how long it takes you to even know there's a problem. If your MTTD is high, it means your users are your monitoring system.
Which is the worst possible situation.
The worst. Second, mean time to repair, or MTTR. How long it takes to fix the problem and get the service back to a healthy state. This is what blue-green deployment is designed to crush.
And third,
Mean time between failure, or MTBF. The expected time until the next failure happens. This is what drives you to invest in better architecture and more redundancy.
let's apply this to a real risk scenario. Say you have a big database that historically fails about once a quarter.
Okay, so our MTBF is 90 days. Let's say our monitoring is great, so our MTTD is 5 minutes, and the old failover system took 10 minutes to recover.
Now, the team rolls out a new, more complex system. And because of its replication, it doubles the failover time. So the new MTTR is 20 minutes. And because we're deployed across 3 zones, a single failure only impacts 1/3, or 33% of users.
Okay, so now we can quantify the risk of this new system.
Yeah.
The values become MTTD, 5 minutes MTTR, 20 minutes MTBF, 90 days, and the impact is 33%.
And that 10-minute increase in MTTR might not sound like a lot, but when you quantify it, 33% of your users are down for an extra 10 minutes every 90 days. That becomes a real business case.
Exactly. You now have a clear metric showing that the new system is riskier in one specific way, which justifies spending engineering time to automate that failover and get the MTTR back down. It moves the conversation away from feelings and into data.
This is where SRE gets really subtle. What about when the service is technically up? It's returning a 200 OK. But the user experience is awful. The service is in a degraded mode.
This is the classic trap of simple availability metrics. Think about a complex homepage. It loads, but maybe the recommendations widget is broken or the stock ticker isn't updating.
So a simple availability SLI would say 100% available because the page loaded. But the user is unhappy.
Right, and maybe they can't even complete their task because the broken widget was the add to cart button. So simple availability is not enough. You have to use a quality SLI.
And how do you define that?
A quality SLI is defined as the ratio of non-degraded responses to total responses. It measures whether the response we sent was actually useful and complete for the user. It correctly captures that dissatisfaction.
Okay, what about latency SLIs? The target is, say, our homepage has to load in under 100 milliseconds. How do we calculate that SLI properly?
The recommended way is actually very direct. It's not about complex percentile math. It is. Count the number of homepage requests that load in under 100 meters, and then divide that by the total number of homepage requests.
So it's just a simple percentage. The percentage of successful, fast requests. That's much easier to explain to a product manager.
Much easier. It's direct and it's actionable. Now, once you have your SLIs, the things you measure, you need to set your SLOs, your targets. And the target should never be 100% perfection.
No, because that's infinitely expensive and impossible.
Correct. Your SLO should be slightly more aggressive than your current satisfactory performance, but not so aggressive that you miss it on day one.
Can you give me an example with percentiles?
Sure. Let's say you observe that your 90th percentile latency is currently 120 milliseconds and 95th is 275. A reasonable SLO to publish would be to set the targets a little higher to give yourself a cushion. Maybe 90th percentile under 150 meters and 95th under 300 meters.
Why the cushion? Why not just commit to your current best?
That cushion is your error budget. The gap between your observed performance and your published SLO is your capacity for controlled failure. And the error budget policy is a critical cultural tool that you have to agree on before an incident happens.
And what does that policy say?
It dictates what happens when the budget runs out. It says that if the service misses its SLO and the error budget is gone, the development team must stop working on new features and shift their focus to improving reliability.
It's a circuit breaker.
It's a circuit breaker that prevents the death spiral of shipping new features on top of a system that is actively falling apart.
We've covered the tech and the math, but it all comes back to culture, doesn't it? That continuous loop of practice that makes sure we actually learn from our mistakes.
It has to. Otherwise, the best schools in the world won't save you.
So, pre-launch reliability. When does the SRE team need to get involved with the new product?
They must be involved early in the design phase. They need to review the architecture and provide feedback before a single line of code is written. It's called a production readiness review. If they determine a service can't meet its proposed SLOs, they need to identify the reliability work that has to be done before it can launch.
Okay, fast forward. An incident hits.
Yep.
We've declared our incident commander and our leads. What is the very next thing that has to happen?
Before anyone starts investigating, you must establish a communication channel, a dedicated chat room, a video bridge, whatever. You need a single place for responders to coordinate so they aren't working in silos.
And what about the communications lead? Their job is high pressure.
Their job is to provide periodic updates to all stakeholders, internal and external. And the most important rule is that in every single communication, they must commit to a next update time. Even if the update is no new information, people know when to expect the next one, which reduces anxiety and cuts down on distracting pings.
The incident is over. We move to the postmortem. This is the cornerstone of SRE learning.
It is. The postmortem document has to be detailed. Root cause, resolution, lessons learned, and a prioritized list of action items to prevent it from happening again. It needs to be shared widely and critically to support that blameless culture. It must not list the people who are responsible.
You fix the systems, not blame the people.
That's the core of it.
And the final piece of the loop, making sure this specific failure can't happen again.
If the incident was caused by a software bug, the most effective action you can take is to ensure that new test cases that specifically catch that type of error are written and added to your CI/CD pipeline. You codify the lesson. You make prevention an automated, systematic part of your process.
That was an incredible journey through the deep technical flow of DevOps. We've really covered the full loop here.
We really did. We started with the foundation, GitOps, and why you need to manage your Terraform state in a central place like cloud storage. We talked about that 3-repository structure for enterprise scale.
Then we moved to the factory floor, automating the build with high-quality CI/CD pipelines and cloud build, making sure we're caching, tagging correctly in artifact registry, and even using those immutable SHA digests for safe rollbacks.
And then the critical part, the deployment traffic cop. We broke down the differences between the instant rollback of blue-green, the phased risk mitigation of Canary testing, and the ultimate safety of shadow testing.
And we wrapped it all up by defining success with the math of reliability, using MTTD, MTTR, MTBF, and understanding why a quality SLI is so much more powerful than a simple availability metric.
At the end of the day, the core takeaway is that all of this complexity, the Kubernetes RBAC, the partition updates, all of it all serves one single powerful purpose.
Which is?
It lets companies release software constantly, gaining a massive competitive advantage without ever breaking the user experience in a catastrophic way.
And that really leaves you, our listener, with a final thought to chew on. We learned that expert-level SRE often means accepting a degraded state, that homepage that's missing a widget, and measuring that degradation carefully, rather than just waiting for a total failure. So the question for you to take back to your team is this. In your next project, how will you define that specific measurable line where degraded ends and failed begins? And how will your SLIs, your dashboards, and your alerts reflect that absolutely crucial distinction?
Something to think about this week. Thanks for diving deep with us.